All right, so welcome Math 13 students. This is a review of chapters 5, 6, and 7. Come with me while I share my screen. Where are you? There you are. All right, so I'm going to start you from the beginning. And there we go. All right, final exam review, chapters 5, 6, and 7. And as I say, I've got examples embedded here, and I'll be sharing calculator keystrokes as we go through. Now, once again, as I said last night, this is not an attempt to reteach this material. It is really just an attempt to remind you of the detail that we've looked at this semester. All right, so let's begin with chapter 5. In fact, we're going to go ahead and review chapter 5, then 6, then 7. I'll remind you chapter 5 was discrete probability distributions. Chapter 6, normal distributions, and chapter 7 began inferential statistics with the construction of confidence intervals for means and proportions. Chapter 5. Here is our vocabulary. You've seen this vocabulary before, so I'm not going to go over it in detail, other than to point out the range rule of thumb at the very end has been with us for a while. That is the mean plus or minus 2 standard deviations of your data set when estimating significantly high or low outcomes. And in fact, we're going to augment that rule of thumb with a probability notion a little bit later tonight. So here we go. And I'll remind you those significantly high number and low number of successes were important to figure out when things of import happened a little bit further on in the course. We also took a look at a binomial probability distribution, and I'll be reminding you of all of that as we go through this material. All probability distributions have these following requirements. The sum of the probabilities must equal 1, and each probability must fall somewhere between 0 and 1 inclusive. Now, a probability distribution has parameters just like a population. There is a mean mu, a standard deviation sigma, and a variance sigma squared. Now, I've included the formulas here just because I had spent so much time earlier this semester getting my computer here to do these things. But in all honesty, our calculator handles this calculation for us, and there's no real need to use any of these formulas. But they do look impressive. Here's an example of just such a thing. We're going to use the given probability distribution. It will appear there in a moment. We want to find the probability that x is exactly 2. We want to find the probability that x is at most 2. And then we want to find the probability that x is at least 2. Although I believe I left that third one off. We'll see. So there's the probability distribution. You have your discrete random variable x, and it assumes the values 0, 1, 2, or 3. You have the probabilities there. They do sum to 1, and each of those probabilities falls between 0 and 1. So that's the work we will work with. So let's go ahead and take a look at the first two. I think I did leave that third one off. We want to find the probability that x is exactly 2. And then we're going to find the probability that x is at most 2. So the probability that x is exactly 2 is no more difficult than reading that directly off the probability distribution. It was a 0.010. I believe that was the case. Let's see. 0.010. Now, to find the probability that x is at most 2, that means x could be either a 0, a 1, or a 2. So I need to look those probabilities up directly on that table, sum them together, and I get the 0.635. So A lot of issue that students face with this type of problem is working with the language, at most 2, less than 2, at least 2. Things like that tend to assume a little bit of import as we work through this, and it can be confusing for students. We're going to use that same distribution and find the mean, the standard deviation, and the variance. And then we're going to use those values to identify significantly high and low x values. All right, now this is where I need to stop sharing here and jump on over to my calculator and share that screen. So here we go. And I believe I have that data entered in list 1 and list 2 on my calculator. So stat to calculate, and depending on how your calculator is set up, second list 1, comma, second list 2. And these keystrokes are available in any number of videos that have posted on our Canvas course shell over the course of the semester. So there we go. I have a mean, an x bar of 1.615. I have a standard deviation sigma of 1.1 and change. And I will note that the S is empty and I only see the sigma. That is because my calculator knows I am working with a probability distribution. So let me stop my sharing here and jump back to the slideshow. So there was the mean of 1.6. There was a standard deviation of 1.1. I'll come back and pick up the variance in just a moment here. And then I took these values and I started with the mean and I added and subtracted 2 standard deviations. I didn't bother completing this calculation. You've seen me do this any number of times. You subtract and then you switch the minus to a plus and you add. So let me jump back to the calculator and we'll go over the keystrokes to pick up the variance. And this is one of the keystrokes that I do know students find a little bit confusing. I go to the vars key, which is where my calculator stores all the values that it uses in any of these little programs that it's got running all through its little system here. I pick up the sigma, not the S, the sigma, and I hit x squared, which adds the square to the sigma x value. And there we go, 1.216 and change, 1.2 when I round to 1 decimal place. That's 1 more decimal place than the x values, which were whole numbers. So that is where all of those values come from. Ideally, it's the keystrokes are relatively straightforward and the data sets are not overly large. Some definitions. Let's talk about a binomial probability distribution now. A binomial distribution is a distribution of outcomes and related probabilities. It's got to satisfy these requirements. And I really want to emphasize these requirements here. I don't believe I asked you directly about them on the exam, but they must be met for the calculator really to give you reliable results. Not that we honestly spend a lot of time relying on our calculator to make important decisions, but we need a fixed number of trials. The trials must be independent. The outcomes have to be classified in 2 ways. And the probabilities must not change from trial to trial. So here's an example. There is a 0.85 probability, p equals 0.85, that a randomly selected adult has heard of Twitter. We are going to use, I've got the wrong program in there, Binomial 83 program. No, we're going to use the binomial PDF and CDF. To find the probability that when 5 adults are randomly selected, exactly 3 have heard of Twitter. And then we're going to calculate what is the probability that at least 3 have heard of Twitter. Let me escape this for just one moment. I thought I had, it kind of bugs me. I thought I had all the fluff removed. All right, we're going to leave it at that for now. We're going to bring it back here. Where are you? There you are. Okay. So we're going to use our calculator to find the probability that when 5 adults are randomly selected, exactly 3 have heard of Twitter. And then we're going to find the probability that at least 3 have heard of the Twitters. All right. So let me run over the keystrokes. Let me stop my sharing here. And I will remind you that your calculator is capable of working with binomial distributions. That's under our distribution key. We've used it quite a bit this semester. PDF for exactly X number of successes. So that's going to be my first stop. And CDF for the at least part. So let's see. Let me quit here. Yeah, let me try something here. All right, so how many trials did we have? We had 5 adults were selected. Any one adult had a probability of 0.85 or having heard of Twitter. By the way, another way to think of that P is that 85% of adults have heard of Twitter. The exact X value, 3. We can go ahead and we can paste that into the function. And there we go. There is the probability, 0.138 and change, 3 significant digits, 0.138. So let me stop my sharing and come back over here to the PowerPoint and just make sure that that we are in the right ballpark. And I've identified the N, the P, oh, I've got a typo there too. Darn. I probably shouldn't use this as my opportunity to fix that. I'll fix it later. It should be a 0.85 there. It's really kind of funny because I only pick up on those when I start to read them out. All right, so we took care of that first one. 0.138 is the rounded version of 3 significant digits. I've got 4 there. Now, let's take a look at this one right here. This is the probability that at least 3 of the 5 adults selected have heard of Twitter. This is a sum of many. That means I need to know the probability that X could be 3 or 4 or 5. Essentially, it's the addition rule for probabilities here, and it's a sum of many. So this is really what I'm going to be seeing once I take a look at my calculator. Now, here's the issue that we face with our calculator. When I put in the trials and the p-value, and it asks for the X value, it's important to remember that this is a from 0 up to. So if I place 3 in here, I'm going to get the wrong result. So watch. Let me go ahead and paste that in there with a 3. That's not the correct result. No. I need the complementary argument. I need 1 minus, and then I'll go ahead and pick up the cumulative distribution function. And at least 3 means the complement is 0, 1, or 2. So this is what I'll go ahead and I'll place into the binomial CDF function. And there's a 0.93973 and change. So we need the complementary arguments when we work with the some of the cumulative polynomial distribution questions. That can be a little bit tricky. If it's at most, then it's no problem. You put in 0 and you put in your upper value and you're good to go. Again, take a look at some of those other videos. We have a bunch of examples there. So there's our second outcome. The binomial distribution also has parameters. And this honestly is one of the very few places this semester where we actually need to use formulas. So if we have a binomial distribution with n and p and q, we need to use formulas to find the mean, the standard deviation, and the variance. The mean is equal to n times p. The standard deviation is equal to the square root of npq. And the variance is the square of both of those guys. So it's just, excuse me, n times p times q. So as I say, it's important to remember that this is one of the few places we actually need these formulas. So unlike a little bit earlier, when I had those other formulas up there that we didn't need, these we need. And as I point out, we need to know the number of trials. We need to identify P, and we need to identify Q. Q is equal to 1 minus P. We've used this formula in one form or another since chapter 3 in our discussion on complementary events. And I do note here that sometimes P is provided, and sometimes we must provide the P. And if X is a whole number, we usually round our parameters to 1 decimal place. And I'm hard put to think of a time in chapter 5 here where we don't have whole numbers for X's. Here's an example. So based on the Harris poll, 60% of adults believe in the devil. Find the mean and the standard deviation of the number of adults in a sample of 400 that believe in the devil. So if we use those 400, we have our n, and the 60% gives us a p of 0.60. And we can provide q, 0.40. Remember, p and q have to add to 1. So those are the values I actually need for my formula. 400 times a 0.6 is 240.0 adults. And when I put the n, the p, and the q inside the square root and find their product, I get 9.8 adults. And there we go. It's really that straightforward. And now once I use, or once I have access to those, I can go ahead and again use those values to find the level for significantly high and significantly low values. So I say 2 sigma rule there, but that's that rule of thumb, the range rule of thumb. There we go. So let's see. So based on that problem, would it be significant to survey those 400 adults and find only 215 had expressed belief in the devil? So we identify the limits of the usual outcomes. 240 plus or minus 2 times 9.8. At the low end, 220.4. At the high end, 259.6. So you'll note in that cute little picture there that x equals 215 is indeed below 220.4. So it would be 215 adults would be a significantly low number to find in a survey of 400, and it might indicate some larger change in belief in the population about the devil. Yeah, it's kind of a cute little problem, but it really gives the flavor there. Now, we also have a way of dealing with this in terms of probabilities. If the probability of X or more is less than a 0.05, that will be a significantly high number of successes. X or less than 0.05, that would be a significantly low number of successes. So you need a probability, but that probability is compared to a 0.05, kind of a picked at random number, honestly, but it does really work well for our purposes here. Those probabilities are the sum of many in the fashion that we just looked at previously. In fact, if we go back up to that previous question, none of these fell into that category of less than 0.05. These probabilities were all distinctly greater. Come back, where are we? There we go. So this comes up in a number of different places. Most directly, this type of argument is also the basis for level of significant arguments and the like in chapter 7, 8, and beyond.
Oh my gosh.
So, and we can kind of double check our work, and we can use the probability to determine if only 215 adults who express belief in the devil is a significantly low number. So again, I need to change the name there, but it's a sum of many. And you'll note that this one begins at 0 and it ends at 215. So this is a count up from 0. So when I handle this problem, this time I don't need to do the 1 minus because I can use the trials 400 p 0.60 that's at 60%, the X value 215. Paste that in there, and there's a 0.00647 when I round to 3 significant digits. So I can look at that in terms of a plus or minus 2 standard deviations from the mean, or I can look at it in terms of probability. And they really should support each other. I really shouldn't get diverging opinions there, unless there's something odd going on. All right, so that's the chapter 5 material. Chapter 6. This is where we got a look at the standard normal distribution, critical values, z-scores, and the sampling distribution, particularly for a mean. That was our detail there. We used a couple of different programs. We also took a look at uniform probability distributions, but they will not appear on your final exam. But your standard normal one probably will. So we want to find the probability that a randomly selected z-score falls between -1 and +2. And I always tell students it's always important to draw and label your graph or your quick picture before reaching for your calculator. So there's my z distribution. It doesn't have to be anywhere near that precise for our purposes there. You just need to be able to identify the lower and the upper limit. I will also remind you about the mean and the standard deviation. You can see there the mean is 0. What's the standard deviation? The standard deviation is 1. So let me go back and pick up my calculator again. And distributions. and normal CDF. We never even used the normal PDF, by the way. The lower bound, I believe that was a -1. I get an error when I do it like that. The upper bound was a +2. The mean is 0. The standard deviation is 1. We paste that in there. And there's the 0.818 and change, 0.819 to 3 significant digits, although I bet I got 4 on that other screen. Oh, wait, that's the wrong one. Sorry. There we go. All right, so drawing and labeling, there we go. And there's that probability. 819 to 3 significant digits. Really, a quick picture is so helpful there. Values or scores determined by area are called critical values. And the critical values, they may be z-scores, usually written with a z alpha over 2, although not always. Or for other continuous random variables, they may be actual values, like an SAT cut score, for example. So this time we're going to find the z-score that separates the bottom 10% of scores from the rest. We want to identify the region that corresponds to the bottom 10% and identify what part of the graph we're looking at. Is it part of the left tail or the right tail? So it's the inverse normal 83. No, that's the wrong program again. Let me go ahead and pick up the right program. I thought I picked up all of those. Gosh, that's annoying. This is where we get to use our inverse normal function right there. The area I am interested in is 10%, so 0.10, 10%. There's the mean, there's the standard deviation, and we're working with the left tail. There it goes. If you don't have access to one of these plus CEs that give you the option of left tail, it works like the binomial CDF function, counting area up from the far left to whatever stop point you have. So on occasion, if that is the case for you, you might need a complementary argument. So a -1.282, I'm going to take 3 decimal places there, I believe. And that enables me to -1.282. That's that z-score there. So another example. IQ follows a normal distribution with a mean of 100 and a standard deviation of 15. We want to find the probability that a randomly selected student has an IQ that is greater than 115. So this time I have a normal distribution. It's not the z distribution, and I'm asked to find a probability. This is where students would be expected to remember that it's a question about probability, and it's the normal CDF tool that we want to use here. So 115 greater than 115. All right. So lower bound, 215. The upper bound, I'm sorry. I got to jump back for a second. 115. Geez. Try that again. The 215 did not seem right. Let's see. There we go. 115. I was still thinking of that other problem for some reason. Upper bound, 10 raised to the 9th. Mean is 100. Standard deviation is 15. Paste that guy in there. And there's the probability, a 0.1586159 to 3 significant digits. So where are we? Here we are. There's the 159, and there's the pretty little picture. So the probability that the IQ might be greater than 115 is 0.159. Another way to look at that is that about almost 16% of people, of all people everywhere, have an IQ greater than 115. Another example. Oh, pregnancy, the miracle of birth. It's normally distributed. The mean is 280 days, and the standard deviation is 15 days. So we have a couple of questions here. What lengths of pregnancy separate the longest and shortest 5% from the rest? And what length of pregnancy separates the shortest 1% from the rest? I'll remind you that short pregnancies can lead to babies that need lots of very important care very early in life. So I want to identify the cut scores for the bottom and top 5% of pregnancy length in terms of days. The total area is 10%, but the area for each tail here is 5% or 0.05. So since I'm after a score, it's the inverse normal tool I wish to use now. The area, point. Now you've got a couple of options here. My calculator has the ability to select center. So I'm going to type in 0.90. That's everything except the 10% allotted to each of the two tails. 280 days and 15 days for the mean and the standard deviation. There is the center. So paste that in there. And there we go. At the low end, I'll round to the nearest day. 255 days. At the high end, 305 days. 280, kind of smack dab in the middle, if you. So let me come back over here for just a moment. There's a 255 and the 305. Now, if your calculator does not have that left-right center, it is still quite possible to do this. You've got to be a little bit tricky here. Let me let me jump back just one screen here to here. There's 5% of area over here. There's 5% of area over here. So let me stop my sharing and come back over here to my calculator and develop both of those in a slightly different fashion. So inverse normal, area 0.05. There is the mean. And if you don't have your, in fact, hold on. Let me do this. We turn that off. Okay, quit. All right, so if you have one that gives you this, so now what you want to do is to type in the 0.05, comma, 280, comma, 15. Don't worry about the center, close them up. And now I'll get the 255 and change. This gets me to the that left endpoint, if you will. A second bite at the apple. This time I'll use 0.95. So that's all the area up until that cutoff on the far right, comma, 280, comma, 15, close them up. Now I'll get the 304 and change. And there it is. So you may have to think your way around the problem like that if you do not have access to that left, right, center option. But in any case, it's imminently doable. And you'll end up with the longest and shortest number of values there. Now, the shortest 1%, there's my left tail, 0.01, strictly left tail. This time it really doesn't matter. I'm going to keep it in this particular mode here. 0.01 to 80, 15, close. And 245 days would be the cutoff for babies in the bottom 1% of pregnancy length. And hospitals truly have a need for this type of calculation because they need to have special special equipment on hand. So they'll need to know what the cutoff date is. They'll need to know how many babies they can expect. There's any number of reasons they need this kind of data. Now, let's talk about the central limit theorem. Oh, wrong way. There we go. And I'm going to run over the detail here, but I do want to keep the example simple and straightforward. Random variable x has a distribution with a mean mu and a standard deviation of sigma. That's just no new news. That's what we expect for a population. There are no real requirements that the distribution be normal. And samples of the same size n are selected. That's the setup. The actual statement says that as the sample size increases, the distribution for the mean will approach a normal distribution. And the mean of that sampling distribution, if you put all those x bars together in their own little distribution, the mean will approach the true population mean mu. The standard deviation of that sampling distribution approaches the value sigma divided by the square root of n, where sigma is the population standard deviation. And there was a bit of an issue. If n is greater than 30, then the population for the sampling distribution is normal, and you get to use the formulas and the theorem straight away. If the underlying population is normal, then the sampling distribution will be normal for any size. If your sample size is 30 or less, you really cannot use this theory at all without knowing something about the population distribution. And I wanted to remind you of the funky ass notation here, the mu with the x bar in the corner and the sigma with the x bar in the corner. And we actually have need and use these these formulas on some of our problems. In fact, I'm going to use it in just a moment or two. Here's my example. So IQ is normal with a mean of 0 and a standard deviation of 15. Samples of size n equals 25 are selected. You'll notice that because the population is normal, I don't care that I have a sample size smaller than 30. And we're going to do two versions of this problem. The first version, n is going to take the value of 25. We're going to find the sigma x bar and the mu of x bar, and then I'm going to up the ante and let n equal 100. And I'll be able to point out some of the detail. So again, if you know the sample, or excuse me, the population mean, you know that sigma x bar, excuse me, mu of x bar. So since you know that the population has a mean of 100 for IQ points, the sampling distribution will also have a mean of 100. The standard deviation, on the other hand, is calculated by taking the population standard deviation of 15 and dividing it by the square root of the sample size. So you can see that the sampling distribution will have a standard deviation that is much smaller than the population standard deviation. In fact, if you're working with a sample of 100, the standard deviation is now 1.5, very, very small. That means there's not much spread in the data, and that's usually a very good thing when we're trying to use inferential statistics. So bigger is better, it's the truth. And I put together a little montage of pictures here to show exactly what happens as the sampling size increases. The population distribution is normal and has a mean of 100. The sampling distribution is also normal, but it's with a mean of 100, but the standard deviation is 3. So the distribution takes on that form. You can see that it has less quote unquote spread than the previous example. Then, if we have a sample size of 100, we have a sampling distribution that is really quite quite centralized around that mu of x bar equals 100. So here's a visual representation of what happens to the sampling distribution as that sample size increases. So length of pregnancy, approximately normal. We've already used the 280 and the 15 days for the mean and the standard deviation. So we're going to select samples of n equals 25. Here's the question. What is the probability that the mean x bar is more than 287 days? Not a randomly selected pregnancy, but that the mean of that sample is 25 is more than 287 days. And then I'm going to compare that result to the probability that a randomly selected pregnancy lasts more than 287 days. And this is really what gives us the ability to engage in inferential statistics. So sample sizes of 25. It's a central limit theorem question. The mean is 280 days. The standard deviation is 15 divided by the square root of 25, or 3 days. So I can see I need to do some work with this. There's a typo up here too. Oh, good Lord, go away. I'm not ready for you yet. So let me come back to my programs, because I think I got a typo there. Gosh. Where are you? There you are. Okay. So I'm looking for a probability distribution. Normal CDF. And actually on this one, I really want to go back to my stat wizard, because I can emphasize that standard deviation formula. So the lower limit, 287 days. The upper limit, 10 raised to the 9th power. The mean, 280 days. The standard deviation, 15 divided by the square root of 25. Close them up. And you can put him in there like that. You don't have to put him in there as a 3. And if you can see it as a 3 and you want to do that, right on, that's righteous. But your calculator will do the arithmetic for you also. So now I will do the paste. And the probability that a randomly selected sample of 25 has a mean pregnancy length of more than 287 days. 0.0098, well, 982 when I round to 3 significant digits. Now let me see what I've got in that picture. I think that picture's jacked up. There's the 287 days. There's a 0.098. I think it's just this 115 that's the typo. Should be 287. So that is really the key to it. And as I say, your hard goal will be to identify this question as a central limit theorem question. All right. Hey, Aiden, can you hand me my my sling for my arm? It's over there on the sofa. Thank you. It's my son. He's going to give me a hand here. As I was saying, your real chore here is to identify this as a central limit theorem type of question. And the only real way to do that, let me come back to the question. When selecting samples of size n equals 25, that is the fundamental detail there that you need to pull out. It's that, what is the probability that the mean is more than 287 days? The mean. And if you don't pick up on that word mean, you'll probably end up doing the second question. So that's the first one with the probability for the sample mean. Oh, but I didn't do the other one. Hold on. Let me go back to my calculator. I threw these together from previously made PowerPoints. So we're going to do this again. $287, but here it's just going to be 15, not 3. So you can see the probability that a person's pregnancy might last longer than 287 days is quite a bit higher than the probability that its whole mean will have, or whole sample will have an average higher than 287 days. And it's really that we rely on, and it enables us to engage in the inferential statistics. So as I say, that's what we're going to do right now in chapter 7. I might run a little bit over here, but not long. We have some vocabulary, point estimate, the confidence interval, the level of confidence, critical values, margin of error, degrees of freedom. So we can construct a confidence interval for a population proportion using your TI-84. Using the one prop Z interval tool. I need to supply X and N in the level of confidence. In a study of an allergy drug, 175 of 202 subjects reported experiencing significant relief from their symptoms. We're going to find the point estimate, and then we're going to construct the 95% confidence interval. And if I have time, we'll write it in the p hat plus or minus e form. We'll use my calculator to do that. So the point estimate is your p hat. 175 out of 202. Oh. There we go. So 0.866 or 0.866. So about 86.6% of people experience some significant relief. That's my point estimate. I'm also going to construct a 95% confidence interval, and then I'll use that detail to form the final result. not second. There we go. Sorry about that. Stat over to test. One prob z interval. X bar was 175. N was 202. 0.95 was the confidence interval. And now we'll hit calculate. And by the way, running the one prob z interval also gives us our p hat. So if I know that beforehand, I can just come right to here and get my p hat and my confidence interval. I'll take 3 significant digits here. And so there's a 0.866, and there's a 0.819 to 0.913. So how do we come up with the 0.866? I need to find the 0.047. And I got a couple of ways of doing that. 0.913 minus and there's a 0.047. I could also use the 0.866 minus the 0. Whatever that other number was down at the lower end. In any case, there's my plus or minus value, and I put that together with the point estimate to get the 0.866 plus or minus the 0.047. And this is a very common way to present this type of data. Now, we also had in this section an interpretation here. We have a level of confidence that the interval contains the true value that we are interested in. So in this case, we are 95% confident that that interval, 0.866 plus or minus 0.047, contains the true population of proportion of those experiencing significant relief from their symptoms. And that's the mouthful. Will you have to regurgitate that kind of mouthful? No. But that's exactly where it needs to go. Now, there was one other topic, and that was the topic of sample size. We wish to determine the percentage of traffic stops that result in an arrest, and we need to determine a sample size before we can get on with our study. We're going to use a 95% level of confidence when we develop that confidence interval. We want our true estimate to be within 3% of the population proportion, and no prior data exists. This was another time we actually needed a couple of formulas. Those were the sample size formulas. So the question is, which formula? Well, it's the one with the 0.25. What I will need is a critical value, the z alpha over 2. And then I need that margin of error. So let me stop my sharing and get my critical value. Inverse normal area. I'm going to be building the 95% confidence interval. So that means there's half of 5% on either side, but 0.95 right in the middle. The mean. Dear, what was the mean? Let me come back here for a second. Okay, there we go. Okay, so we leave it in the z-score format, and I'm going to get 2 scores here, and negative and positive 1.959, 1.96. plus or minus 1.96. And let me come back over to my other screen and I'll remind you that the Z alpha over 2, 1.96, my margin of error is 3% or 0.03. I don't even worry about the negative one. I'm going to just take the positive one and square that. And there's a 0.25. And my value is the 1,067.111 and change. Now, in addition to everything else going on here, there was a crazy ass rounding rule when it came to sample size. It calculates a minimum size and it must be a whole number. So fractional sizes must be rounded up to the next whole number. So if I was studying traffic stops, 3% margin of error, and I wanted to be 95% confident in my outcome or my interval, I'd be looking for at least 1,068 people. Now, that is truly a challenging question for my students. It is at most 5 points on a 200-point exam if you do run into that over the course of the next couple of days. Now, the last part of chapter 7 that we covered was much easier. We wanted to construct a confidence interval for a population mean. And I can do that again directly. This time I use the T interval. I can supply X, S, and N, or raw data and the level of confidence. We use the T distribution here, but it's built into the tool. So 40 randomly selected students took a calculus final. You'll notice that N is greater than 30 there. And the sample mean was 78.2 and the standard deviation was 7.5. We want to construct a 95% confidence interval for the mean score for all students. So 7.5 and 8.2. So, sorry, 78.2 and 7.5, and we've got a sample size of 40. I'll probably forget by the time I get to my calculator. T interval. I could use raw data, in which case I'd be pointed towards a list, but I've got stats. So 78.2. The standard deviation, I think, was 7.9. The sample size was 40. And I'm going to go with the 95% confidence interval. It's always the most popular. And there we go, 75.7. I'm going to take one decimal place. I want it the same as my X bar. There's my point estimate, by the way, 78.2 and 80.7 on the high end. So let's see. Oh, 7.5. I use 7.9. My answer is a little bit wrong. So let's see. Let me come back over there and change that. One of the nice things about doing these kind of problems on your calculator, if you do make a simple mistake like that, you come back over to take care of that little guy. Very easy to fix. So there we go, 75.8, 80.6. And there we go. So you've seen me do those plus or minus a couple of times already. You should be fine there. So we are 95% confident that the interval 78.2 to plus or minus 2.4 units contains the true mean final exam score for all of these students. And I only looked at 40. There we go. That really does bring me to the end of my review for chapters 5, 6, and 7. How did I do? Oh, it's 7:33, 3 minutes over. But I started 3 minutes late. So there we go. Let me stop my recording.